Welcome, everybody. In this video series, we're going to talk about, or I'm going to show you how to set up a plastic analysis in ANSYS. So I have here geometry from a previous video. We're going to reuse the notched bar for this example. So that geometry is here. So the first thing we're going to do is grab the static structural and drag it over to our green box. And then I'm going to click on the geometry, left click on the geometry, and drag it over to share with our static structural analysis. Now I want to go over the geometry real quick, so I'm going to right click, edit, and then I'm going to click on edit geometry and design modeler. So I've shortened the notch bar from the previous video just because we're limited to our node count. And I've also sliced it. So I've sliced it by the YZ plane. And the reason why I did that is so that I can use Symmetry to model just half this bar. And then you can see here I've sliced the model so that there's three bodies. And again, if you're doing an analysis in ANSYS, what you want to do is make sure all of your bodies are as one part. So you would right click here and click form new part, but they're already part of our part, so we don't have to do that. Next, I'm going to right click on the model and click edit. And we see our static structural analysis. And I'm going to make sure our units are in inches because I've been working in the US customary units. Now I'm going to go back and I'm going to add our materials for the plastic analysis. So I'm going to left click on engineering data. And I'm going to go over here and I'm going to right click and left click on engineering data sources. And ANSYS has a library of nonlinear materials, which is required for the plastic analysis. So I'm going to use the aluminum alloy NL, which is nonlinear, and I'll click the plus button. And then I'm going back here, and you see that our material is populated. So I wanted to talk real quick about this. If you have a nonlinear material, you'll see here in this case, this nonlinear material is using a bilinear isotropic hardening to represent the plasticity. And this is based on the true stress and strain curve. So if I left click on that, so I've gone up here and I've clicked on the yield strength here, and you can see the graph of the stress versus strain, the true stress versus strain, and the bilinear isotropic hardening plasticity model. There is a linear elastic region, which is represented by this slope here, the slope is the modulus of elasticity. And then there's another curve here that's linear. This is the linear inelastic region. So this is based off of the yield strain and stress and the ultimate strain and stress, and that's the true strain and stress. So the next thing I'm going to do is I'm going to copy this material. So I'm going to right click, duplicate, and I'm going to rename this as aluminum alloy linear. And then I'm going to delete the bilinear isotropic hardening. So if you don't have a plasticity model in your material, then ANSYS will run a purely elastic FEA analysis. Now, if you include the plasticity model, it will run the FEA, and if you have localized stress that is in the plastic, or your localized stress is above the yield, then it will use this model to model the plastic behavior. All right, so I'm going to go back to our static structural model, and the first thing I'm going to do is I'm going to assign this part the, well, I have to right-click project, or I'm sorry, right-click model and refresh materials. And now we see that the materials we added have shown up. So for the first part of this, I'm just going to run the material with just the elastic result. Now to set up the symmetry, you're going to go to model and right click insert and come down here to symmetry and click on symmetry. And then we can insert a symmetry region by right clicking on symmetry, going to insert symmetry region. And the geometry selection, we're going to click the faces that the part is symmetric about. And then we're going to make sure that the symmetry normal aligns with where we want. So essentially, this is it's mirroring. It's not quite that, but you could think of it as this is being mirrored about this symmetry plane. And so the symmetry normal axis, we need to verify from our global coordinate system that it's correct. So we go to our global coordinate system and we see that the normal is the x vector, and that is what we want. So that's good. All right, so now we're going to mesh the model. So I'm going to go to mesh and right click insert sizing. And we're concerned about the notch, so I'm going to click on these two edges. So if you click on the first edge, then hit control, you can click on the second edge, and then you click apply, and you'll see that both of them are selected. And I'm going to change the element size to 0.03125. And I'm also going to make sure that my element order is set to quadratic. And I'm going to insert sizing again, and I'm going to click the middle body, click apply, make this 1/8 of an inch. And I'm going to right click insert sizing again, and then I'm going to click the two bodies. I'm going to change that to 0.2. Then I'm also going to do a sweep method. So I'm going to insert method, click the body, and then click apply, and change this to sweep. And I'm going to do a manual source target. Our source will be that face, and the target will be the back face. And then I'm going to change the free face mesh type to all quads. Now I'm going to right click on mesh and click generate mesh. And one thing I forgot in the sweep method, I'm going to change the number of divisions to 16. So I'll clear this mesh and then click Generate Mesh. And we're concerned really about the stress gradient in going from the notch into the part, and what would be the X direction here if we're in the center. So I'm happy with that mesh quality. Now we're going to set up our boundary conditions. So I'm going to click on static structural, then right click, insert force, and click on the top face, click apply. I'm going to define it by components, and we're going to do 100,000 pounds. So 100,000 pounds is going to be applied to half the part. So the total applied load on the whole part will be 200,000. And then if you watch the previous video on the notched bar, the cross-sectional area is 10 inches. So we should get 20 KSI. Now I'm going to set up the constraint, the fixed support boundary condition. So I click the bottom, click apply. And then let's set up our stress results. So I go into right click solution, insert stress, look at the normal stress, and you can look at just a certain face or body. So I'm going to click the middle body and click apply. And then we'll look at max principal and also equivalent. And we'll also look at strain. We'll look at equivalent plastic, total, equivalent total, and we'll also look at the equivalent strain. And so for all of these, we're going to do the middle one, or the middle body. All right, so we are all set. We've got our material is a linear elastic aluminum material model, and we have our symmetry set up, and we have our mesh set up, and our boundary conditions. And so before we click solve, I'm going to go back to the main menu, and in order to view the full bar with symmetry, you have to go into here to appearance and go down and make sure the beta options is checked. All right, now I'm going to right click solve. Let's look at our normal stress. And I have to change that to the Y direction. All right.